Hey there, I'm James, and I'm joined today by Christian and Danny, and we're from the University of Rhode Island. For this competition, we're part of group AS043, and we made a Quantum Gate emulation. The emulation itself was created in the FPGA fabric on the DE10 Nano, and the user controls the emulation through a web app that is hosted by the ARM processor on the DE10 Nano.
In front of us now is the user interface through which users will interact with the quantum emulation. It is a website hosted on the DE10 Nano's ARM chip, accessible by any internet-connected device that has a web browser. On the left of the screen, we can see all of the quantum gates that can be placed onto the blank circuit in the middle of the screen. To keep the operation of the website simple, the gates are simply dragged into any empty slot of the circuit. Likewise, you can remove a gate by dragging it into the trash. When the user wants to send their circuit to the FPGA, they can click the pink play button and view the output on the right of the screen. As we can see from the output, qubits, unlike traditional bits, are represented by a probability of measuring the qubit as 0 or 1. We will talk more about this later. On the left of the screen, we can see that there are three types of quantum components that we can use in our circuits. Base states, which change whether the circuit starts in state 0 or 1, can be dragged to the beginning of the circuit diagram. Single qubit gates, which change the characteristics of a single qubit, can be dragged anywhere into the body of the circuit. Finally, multi-qubit gates, which can act on 2 or 3 qubits, can be dragged anywhere into the circuit where they can fit. All of these components are designed and animated for beginners to quantum computing in mind. All of these gates are unique in design and demonstrate what they can do by their motion. To help beginners build a working circuit, only valid logical actions can be taken within the GUI. As you can see, if you try and place a multi-qubit gate where it cannot fit, the GUI will address this issue. This website is hosted on a Flask framework server running on the board's ARM chip, which allows easy HTTP post and get commands to be sent between the server and website. To make this emulation as fast as possible, every time a user takes an action, JSON data containing the action's context is sent to the server, which in turn calls precompiled C executables capable of reading and writing to the FPGA memory. Only when the user clicks the play button will the server request data from the FPGA memory to display on the website.
So getting into the hardware implementation of our project, we start with how a qubit is represented in hardware. The state of a qubit is dependent on its probability of being in each state, 0 or 1. We use a 32-bit signal broken into 4 8-bit parts, one part each for the real and imaginary parts of the alpha and beta probabilities. We need these 4 parts because the quantum gates operate on the complex representation of the qubit's state probabilities. For our emulator, we implemented 8 classical quantum gates: the poly X, poly Y, poly Z, square root of naught, Hadamard, the controlled knot, and the controlled knot, also known as the Toffoli, and a bypass. Generally speaking, the gates each have their own 2x2 characteristic matrix that are multiplied by a 2x1 matrix containing alpha and beta. The multi-input gates have larger matrices because they act on more than one bit. In our VHDL representation, we update the real and imaginary parts of alpha and beta based on the results of this matrix multiplication. For example, the poly X gate, also known as a NOT gate, has this characteristic matrix. Multiplying by alpha and beta results in the real and imaginary parts of alpha being swapped with the real and imaginary parts of beta. The rest of the gates follow the same principle, which allows us to implement each one with simple combinational logic that can give us an output in one clock cycle. For our circuit setup, we went for a design that functioned as a programmable gate array. Our array consists of 8 columns of 13 gates each. In each column, we have one of each of the 8 gates we implemented plus 5 more bypasses. The C0 gate is a 2-input gate, and the Toffoli gate has 3 inputs, so this brings our total number of inputs to 16. We have a pipeline register between each column to save the results of each of the previous column's gates. Each gate has a multiplexer before its inputs, which allows us to program which of the previous column's outputs should be connected to that gate's input. The operation of the circuit begins by writing a 32-bit qubit to an input register. With 16 inputs per pipeline stage, there are 16 addresses where a qubit can be written. Then one gate must be selected for each of the 8 pipeline stages. The inputs to the gates, the multiplexers, are addressed by 8 bits, 3 of which select the column and 4 select the row or gate. After sending the gate address to the circuit, the input is chosen by 4 bits. After 8 gates have been chosen, the output register can be read to obtain the 32-bit qubit.
With the user interface and hardware emulation designed, the last step for our project was to link the 2 components. This required some method of communication between the web server and the FPGA fabric. The QSYS system design tool, which is part of the Quartus 2 software, allowed us to create external input and output signals to the emulation circuit. These signals could then be written to and read from by using the lightweight HPS to FPGA bridge on the DE10 Nano. In order to integrate these external signals with the emulation, a top-level communication circuit was designed, which facilitated the reading and writing of the different pipeline stages of the emulation. This top-level circuit utilizes external read-enable and write-enable signals for handshaking with the read and write operations. Now, with the external I/O signals defined and implemented for our hardware emulation, the next step was to develop software which could read and write these signals. One design consideration that needed to be made at this stage was how the web server would utilize this software to communicate with the FPGA. After giving it some thought, we realized that all the actions the user can take essentially boil down to 3 basic commands. They can change the state of the input qubits, read the output of the emulation, and change the selected gates in the emulation. This train of thought led to the creation of 3 generic executables which the web server could invoke. Each of these generic executables can perform one of the basic commands as listed above. I'll go into a bit more detail about what each one does soon. So, each of these executables was written in C, and each executable has the same software flow. The memory map of the FPGA peripheral region is opened, some operation is performed using this memory map, and the memory map is then closed. Each external signal to the circuit, as discussed previously, has a memory mapped value that can be written to as well as read from by following the handshaking protocol implemented in the top-level communication circuit. The difference between each executable lies in the operation that it performs using the memory map. One of the executables created is used to change the states of the input qubits. This executable requires command line arguments to indicate the state of the qubit as well as the address of the qubit to update. The second executable that was created is used to update the selecting mux of a specific gate in the emulation, and this executable requires 3 command line arguments to function: the address of the gate, which is specified by a row and column, and the selecting mux value. The final executable that was created is used to read the state of one of the output qubits. This executable only takes a single command line argument, namely, the address of the output qubit to read. This executable returns the state that is read to the web server, which invokes it. With the communication implemented in the circuit, and the software created to communicate with the circuit, the last step was to implement the logic necessary for the web server to utilize the executables. The web server parses the received JSON data and uses this to determine which executable to invoke. In addition to deciding which executable to invoke, the server also determines which command line arguments to pass to the executable so that the generic executables can be used for specific functions. Thank you all for watching our video demonstration. We hope you enjoyed it and we appreciate your interest in our work.